welcome back, everybody. So check it out. We are modeling the atom, and I have skipped Democritus. Okay, we fast forward like 2,200 years, and now we're talking about John Dalton, English physicist who all of a sudden rediscovered Aristotle's ideas. Now, I think we drew a picture of what Dalton said the atom looked like. Okay, it's just in this box. This is the picture of the atom that Dalton had. He said, check it out. Here's a single atom. This is it. Cool. Like, not any different than what Democritus had or had suggested. However, he did take some bigger steps past what Democritus had concluded. So, we know that atoms are what really make up matter. Cool. Matter is stuff, and stuff is made of atoms. Okay, a few more little pieces here. Atoms are indivisible, so we can't break them apart, which we know today is not true, but that is very modern knowledge. Indivisible and indestructible. So we couldn't destroy them. Now, we still have this idea. This is a conservation of mass. Even if we could and do destroy an atom, it changes to some amount of energy that winds up, there's some fancy Einstein math that happens, but we can't break these apart. Now, beyond that, Dalton had a few more additional comments to make. So he said, hey, we have a bunch of these different elements, right? We have hydrogen, helium, lithium, beryllium, boron, carbon, so forth and so on. He said that, hey, atoms of different elements are different. And I'm going to change that wording. Atoms are different for each element. And I'm just going to say for elements. Okay. Few other pieces that I'm not going to write these ones down. John Dalton, he said, hey, everything's made of atoms. We can't divide them down any further. We can't destroy them. Atoms in gold is different than atoms in silver. It's different than atoms of hydrogen, so forth and so on. They're all different to some fashion. Okay, he determined that whole number ratios exist if you have compounds. So we're going to take a brown, don't write it down approach. Anything over here in this box, you don't have to write it down. It's just us talking. What's a whole number? One is a whole number. Can you give me more?
2, 3, 4, 5, 6, 7, 8.
Okay. Now, as we look at these, I would argue these are not the whole numbers. Ooh, you got to include 0 in here. Okay, these are the whole numbers. If you start counting at 1, do you know what numbers you're counting in?
Single.
I mean, you're not wrong. That's true. Is when you are a young child learning to count, naturally you use these thingies, right? Show me the first 5 numbers you learned to count. Everybody started at 1. It is natural. Anybody start counting at 0? Of course not. That'd be a weird thing to do as a child. However, does 0 exist? So really, if we wanted to, we could say 0, 1, 2, 3, right? And we can keep going. As we're through, these are the whole numbers. The natural numbers are what you're probably more used to. Okay, so what he determined is that you're never going to have 1 carbon and half of an oxygen. He said, no, that cannot happen. It's C for carbon and O for oxygen. Not halves, not quarters, whole numbers only. Okay, so last little step. This is a shorthand that we are going to use. We looked at chemical reactions at least briefly. What's the difference between a chemical reaction or a chemical change and a physical change? Changes their composition, which means what it's fundamentally made of is different, right? We are rearranging atoms. And what he determined is that reactions, specifically chemical or physical reactions, which we're going to use a shorthand, and this is accepted. I don't know if I've shown you yet. Shorthand for reaction? RXN. Okay, reactions, are rearrangements. That's it. We rearrange the way that these atoms look. Okay, now, from what you guys know about our physical and chemical world, is anything that John Dalton said untrue?
Yes.
What?
That they're indestructible.
So this part I would say he's definitely true about, but the fact that we have, so it's because, like, if I turn one to pure energy, like in a nuclear bomb, that energy can be converted back and forth between mass, and that's Einstein's big E equals mc squared. That's what that formula actually tells us. All the mass can be energy, and they can move back and forth. You just have to do some fancy stuff. Okay, this part is definitely not true anymore. What did we talk about? Up, down, top, bottom, strange, charm. Quarks. We know that atoms can be broken apart, but that's fairly modern language. Okay, I don't want to go a ton more into John Dalton stuff. Anybody have issues, concerns, thoughts about this? We cool to jump a little bit ahead in time? All right, so Dalton's idea, same as it had been 2,200 years ago, but people accepted it. Okay, we're going to kick forward quite a ways. We're going to go forward 100 years, and I'll switch colors between every one. We talked about John Dalton first. We're going to talk about J.J. Thomson. And I hate this last name. No shade on him. But there's no P in Thomson in his name, and it drives me crazy. Yeah, this guy. Okay, J.J. Thomson. We are now roughly in the year 1904. And a lot of work had been done in the previous 100 years. So this idea of an atom is getting refined. Now, Dalton had this basic idea, and you guys know more than John Dalton did at a true level. You guys know that atoms have positive charges in them, and they have negative charges, right? Okay, what are those negative charges called? So check it out, J.J. Thomson, huge contribution. He discovered the electron. It had never been shown that there were small little negative charges, not discovered electrons. Now, the way that he did this is pretty cool. I don't have one of these. Anybody have an old school TV at your house?
Like the box?
Like a big box TV.
Oh.
Okay, those are CRT TVs is what they're called. And we're not going to go into like how that technology worked, but CRT, it stands for a cathode ray tube. What Thomson did was he figured out a way to shoot a beam of something that we're not going to talk about where it came from, but he shot a beam and it lit up. So he's seeing electricity traveling. Now, he then took a magnet to this beam that's going through a piece of like a tube, and he put a magnet near it. If electrons are negatively charged and I put a magnet near it, what's that beam going to do? It'll either attract or it'll repel. But we're going to see a beam of what seems to be like a laser light bending, right? Okay, that had never been witnessed. Nobody had ever had the idea to connect these two pieces together. He did it. Okay, he discovered electrons using cathode rays. Now, his ideas were not quite complete, and we're going to draw a picture of what J.J. Thomson's atom looked like. So honestly, as long as you're okay with the pictures and the names, like note cards maybe, you're going to be fine for the quiz. Test, whatever the case is. Okay, so I'm going to draw it here. We're going to make one more comment. Here's Dalton's idea. We now know that atoms are small and tiny, and the only thing that he discovered was that there were some negative charges in it. Now, if negative charges exist, but not everything is magnetic, what does that imply must also exist? What cancels out a negative? So he realized then there must be positive stuff too. Now, we know what that looks like today, but here's Thomson's model. So let's say we have this, and it's a lovely circle, and you do not have to shade yours perfectly, but I'm going to go ahead and say, check it out. That is a big ball of positive charge. Okay, everything is positive here. Now, if you look at this, because we're not English people, if I talk about plum pudding, anybody know what I'm referring to?
Pudding made out of plum.
You're probably thinking like regular pudding that's made out of the fruit plums, right? Okay. Now, this is known as the plum pudding model. It is not completely correct, and that's okay. I call it the chocolate chip cookie model, the cookie model. So, what Thomson believed was that all of this right here was kind of like a fog of positive charge. And this is what he thought the atom was, a fog of positive charge, which he's not completely wrong because there are positive charges in atoms, right? What are they called?
Protons.
Protons. So Thomson said, hey, there's negative stuff, there must be positive stuff, and it's in this fog. Fog of positive charge. Now, if this were a chocolate chip cookie, one, it'd be weird because it's red. But I'm also going to sneak in red is positive, blue is negative. And what he thought it existed as is in here, inside of this fog, there's all these little chocolate chips. Or in this case, if you're J.J. Thomson, you discovered electrons, all those little chocolate chips in this picture are the what? These are all the electrons. He thought that all the positive charge was just kind of like this big ball of charge, which is fine. But then he said, hey, check it out. These are the electrons. This is where he thought they lived. And they're just kind of everywhere. E negative. Okay, this model is okay. It's not perfect, but it's much better than Dalton's was. Because he recognized positive stuff, negative stuff, they must exist together. Okay, beyond this, Klein, he also thought that this existed. Okay, is he completely right? Is this what atoms look like? No, he's better than Dalton was though, right? Okay, we are now in Nobel Prize territory, which Nobel Prize is a big prize in what? Science. It's like the prize in science. Now, do you guys know any Nobel Prizes that have ever been won? Bill Nye did not win a Nobel.
Really?
Sheldon Cooper.
Okay, Sheldon Cooper won a Nobel on Big Bang Theory. Anybody pop their knuckles?
Yes.
Anybody's parents yell at you for popping your knuckles? Okay, is it bad for you?
No, I don't think.
A Nobel Prize was assigned, I don't remember the guy's name, this isn't biology. In the 50s, there was a guy that won a Nobel Prize because for 50 years of his life, he popped the knuckles on one hand, which I can't even fathom not popping the other ones because it's giving me anxiety thinking about popping one hand and not the other. But he lived his whole life only popping one hand. He did not develop arthritis nor any ill side effects. He was able to conclude that no, there's no negative detriment to doing this. Now, word of caution. If you pop in your neck and stuff, you run the risk of maybe doing some damage depending on where you're at. Okay, anybody pop their own neck? Okay, real quick, don't actually do it. Anybody do this to do it?
Yeah.
What are you pushing on when you do that? Like, pretend like you're going to pop your neck,
Your jaw.
You're making me want to just
but you're pushing on your what?
Jaw.
Is your jaw really firmly connected to the rest of your head? I mean, it's connected by two little pieces right here, but apart from that, you're running the risk. I've never seen somebody do it. I guarantee somebody has. You could break your jaw by trying to pop. Like, it's better. I can't do it. I do it the wrong way, just so you guys know. You can do it like this. I just pop it there. I don't even have to do anything. All right. Anyway, we now have a model with plum pudding, and I'm just going to write that here, and I know it sounds so silly. This is what he called it. I don't know what plum pudding actually is other than what I've told you. Do you want to take a quick, like, 30-second Google trip and figure it out?
Yeah.
Okay, I bet it's plums. We're going to time travel one more little step, just a little bit further. Okay, we're only going 11 more years. Now, Ernest Rutherford, and I guess 7 more years. Ernest Rutherford. Okay. Ernest Rutherford in 1911 won a Nobel Prize due to his work here. Now, I don't have the names of his assistants ready to roll, but here's the deal. He had grad students. He was a doctorate of physics, I assume. Ernest Rutherford in 1911, he and some grad students conducted an experiment, and they moved the field of physics forward a lot. So what we're going to do is we're going to step out into the hallway. We're going to simulate. Now, I'm going to give you a rundown real quickly, and I'll draw it. I want you to know what happened with it. We're going to visualize this out there. If we were an atom, like let's say that you are a singular atom, we know that all your positive charges aren't really spread equally throughout. They're where? Are they everywhere in real life? Where's a positive charge in an atom?
Oh,
It's right in the ins. Ooh, louder? The nucleus. But cool. So for this, you do not have to sketch this picture for me. But Ernest Rutherford, his big contribution is he discovered the nucleus. So discovered nucleus. Now, he didn't know entirely what it was made of other than the fact that there were some positive charges in it. And we'll talk about how he did it. We'll simulate this experiment. He discovered the nucleus and found out that, hey, there is a super duper dense region within the middle of every atom. That was his discovery. Now, have you guys ever been able to look at the nucleus of an atom?
No.
Have you ever actually seen one, Sonny?
Real life?
Yeah.
Or like in a blueprint?
Nope, real life.
No.
No. If I gave you like crazy expensive microscope, do you think you could? Probably not. So it means that we have to be able to figure this out. We want it to be true physics experimentally. We need to verify these results, which we looked the other day at places like CERN and the LHC where they slam these things together. But that's 120 years moved forward from this. Okay, he had to figure it out that there was stuff densely packed in the middle. And further, we have electrons, remember E negative, flying around. Now, whether or not he was correct here or not is beside the point, but he discovered this. Now, here's how his experiment worked. You do not have to draw this picture, just so you're aware. Okay, he knew, like, in the late 1800s, the Curies, I don't remember her first name. Madame Curie is what she goes by. She and her husband were figuring out radioactive stuff. And, like, terrifying the way that they did it, because the husband would hold something for some amount of time and they'd record about the blisters and stuff that formed on his skin after this, because they were dealing with radioactive material. What do you think happened to Madame Curie's husband?
Cancer.
He died of radiation poisoning and cancer. Cool. What do you think happened to Madame Curie? She died of radiation poisoning. Her notebooks and stuff that she did all of her stuff in, they're in museums, but they're encased in lead because they're still like deadly radioactive today because of how much crazy stuff they were playing with in their lab. They learned a lot, but they also died a lot because of it.
Died a lot.
Well, I mean,
They
they didn't die a little, I can't imagine. All right, so for this, here is, again, totally optional whether you drop it or we're going to talk about it. Okay, we have a lead box. Okay, lead is really, 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 really dense. And the reason that we use lead is because radioactive material can't shoot through lead. Okay, so he has a lead box, and he put some cesium, which is a really, really, really radioactive substance inside of it. Now, it is radiating, shooting off these deadly particles constantly. If it's inside the lead box, it stays inside the lead box. Nothing gets out. But if we put a little hole in this box, now any radiation that escapes is going to come out where? Through that hole. Now, it turns out that radiation, depending on the flavor, which I know it doesn't really have a taste, but there's different types of radiation. Depending on it, there's a type of radiation called gamma radiation that winds up being electrons. That's part of what comes out. Okay, so here we are. He shoots out some particles, and these are all radiation leaving this. Okay, sitting over here, he had some foil, like a piece of gold foil specifically. So here he has gold foil, and it's just kind of hanging out doing its thing. Okay, now it's going to do it all. I don't understand it. I never understand why it does it. Do you guys see an opening in it? Okay, me neither. So check it out. He has some gold foil. Okay, now these electrons and these radiation that's shooting out, if you were to shoot singular little tiny things at gold foil, do you think your eyes are going to be able to see the hole? No. So he didn't either, and that's expected, right? Like this radiation will pass through gold foil, just like it'll pass through us. Like X-rays, do you feel all the X-rays shooting through your body? Are they?
Yes.
They definitely have to be, right? Because it leaves a picture. So he had a special screen wrapped up around this, and I'm going to struggle with my two-dimensional drawing here. Nope, that's close. I'm just going to say here's a screen wrapped around it. I'm going to have to switch to two-dimension. He had, how would this even look? It'd have to do that, right?
Yeah.
And then it would do this, and then you would see it cross over like here. Is that true?
Yeah, that's it.
So it's like a screen going around it.
Oh, that looks good.
Like now that we talk about it, you can tell.
Yeah, yeah.
Okay, so for this, if you were doing this prize and you're expecting that the little tiny beams of stuff that you're shooting are going to pass right through the foil, if we had a substance that would light up when it got hit by radiation, where would you expect all the little lit up pieces to be? Like if you were shooting through, and I'm going to go to, there's very few times where I think it's actually cool and it works out. Where's my star? There it is. Cool. If we're looking at this, is it reasonable to think that these beams keep traveling and they all hit right here?
Yeah.
And you're going to see a bunch of beams there, right? That's to be expected. Okay, because they all pass through. They hit. Now, here's the crazy thing that happened. Most of them, like 99.99999% of the little specks of light, were right behind as you would expect because it shoots right through. However, from time to time, there'd be some places over here that wound up getting lit. Why would these be lit up over here?
They're bouncing off.
They're bouncing off. And they're bouncing off of what? Not the foil. Not the other side. That's a good thought, though. So, like, if we just trace this, and I'm going to go into a lighter thing, and we're going to see this. If I shoot these through, Some of them are going to blast straight through and come out the back and hit right here, right? Maybe from time to time there's a little bit of variation. We get this different paths coming out. Like, that's reasonable, I think. Every once in a while, though, it does this, and it goes boonk, and it shoots off that way. What could possibly lead to that happening?
It loses energy.
It loses energy, maybe. Okay, we're going to cover this here in just a second. We're all going to go out to the hallway. I'm going to have somebody help me carry some stuff out there. We're all going to walk up. I'm going to hand you a jar of marbles first. I need some people to sit underneath with me. We're going to have most people go up to the top of the stairs. I'm going to go grab a hula hoop or something else, and we're going to not cause too much chaos. Cool, cool? All right, so we're going to simulate Rutherford's idea here. So we'll pause. But for 99.999% of even your throws just now, they all did this. With the exception of Guillen's miraculous throw that got one to light up here. Oh, it was you? Oh, I'm sorry. Will you give that aura? Okay, back at it. This was super duper surprising. Now, we have the benefit of knowing what the universe actually looks like today and how these things work, at least better than they did then. If you were doing this and you're expecting empty space, a fog that I just passed through, and then all of a sudden you get deflections that maybe there's one there, maybe there's one all the way over this way, there's only one possible thing that you can attribute it to. The only way that something moving super fast deflects like straight sideways is if you hit something super dense that's just waiting there, right? When we see these deflections, what did these lead to the discovery of? Not just the atom. We already knew atoms existed. These, not neutrons yet. Nucleons, or the nucleus specifically. So we're going to summarize this in a single step. Is that the same color? Close enough. Okay, what I do want you to write down, even if you don't have the gold foil experiment, that's okay. These deflections of beam, which this is the beam of radiation that we're shooting, deflections of the beam imply dense charged center. Okay. Now, this is the basic idea. This is a Nobel Prize. This is the first time that the idea of a nucleus within our atom actually existed. Now, I wish I could remember the name of the other person because this is in England in the early 1900s. There is another fellow in Japan doing similar techniques, similar experiments. I'm going to see if we can find his name real quick because I feel like we should probably include it. That sounds Japanese, but I don't think that's it. We're going to look real quick. Are you guys good at Googling?
What do you mean? I know, because I used
Nagaoka. Okay, Hanataro Nagaoka also apparently discovered this around the same time. That would make sense. They're also from Japan. Okay, so as we look at this, all of a sudden, the idea of the atom got so much clearer because where there was just a fog of positive charge that you could pass through, that was no longer the case. Instead, our model makes a new trip. And you guys might be a little bit too young. There's a TV show about a big head kid, Jimmy Neutron.
Oh, I love
Y'all have seen it? Okay, for those of you that drew atoms in your picture, we now refine this. So here we go. We're going to draw our newest atom. We have this. So no, it's better than this. Okay, this is really dense and what charge? Positive. Here's our really dense positive piece. It's not this big cloud of positive charge. Instead, it's just this. And then whirring around out here, we'll go really faint. And we'll do blue for this. Whirring around out here, we have all these little negative charges, bless you, which these are the whats? These are the electrons. This is the picture that I think of when I think of an atom, even though it's not truly correct. We now have a positive center, a whole lot of empty space, and then really far away we get these electrons. Because the chance of us hitting that positive center is so small, there's a ton of empty space. You, me, everything you've ever touched is mostly empty space, which makes the idea of physics and reality super weird. What you got, Klein? What's up? Yeah, sign on the sheet, okay? Now, this always has made me super uncomfortable. We are mostly empty space. Like 99.99999% of us is empty space. Real quickly, I want you to take the 99% empty space here and the 99% empty space right in front of you, and I want you to just pass through. Since they're 99% empty space, you should just pass through your desk, shouldn't you? So, for this, I mean, there's more ways to be perfect than not, right? If 99% of us is nothing, and it's just empty space between my nucleus and the electrons, there's something weird going on that I don't pass through this. Strange. Now, what that is a bigger question. But check it out. Here's our model of the atom. Are we getting closer to what it really looks like?
That's what I always think of.
How many of you guys think of an atom and you think of this with the stuff moving around in circular paths? Okay, that's natural. Now, we only have two more stops on this path, and we're skipping over a lot of really big names. If this is super interesting stuff, there is a ton of material on YouTube for you to look into. If this is just super boring, good news, we're almost done with it. Okay, so we go Dalton, it's a dot. We go Thomson, electrons exist, and it's like jello. Cool. We go Rutherford and say, hey, it's actually like this. Now, similar here, and I don't know that I really consider these different models. Another big name, and I have no idea if you guys have ever heard this name. Have you ever heard of the name Niels Bohr? Niels, it's Danish, so it looks like it's Niles, but it's Niels Bohr. Okay, Niels Bohr, a little bit more. This is 1913, so only a couple years later. We now know that we have a super positively charged middle. All the electrons hang around outside, and Niels Bohr says, hey, let's make this make sense and connect this to chemistry. So, the new model, he just drew this a little bit differently, and I'll even include a little bit of it because there's reason that he drew this differently. You guys ever seen something produce light?
Yes.
Sure, you've seen lots of stuff produce light. Like you can hit two rocks together to make a spark and it's light. Now, when you see that light, what are you seeing?
Energy.
You're seeing energy. And specifically, you're seeing energy that's leaving in the form of electrons. Now, electric, like sparks and stuff, that's true electrons. But light in general, we have to release some sort of energy, and it happens with the way that our electrons are arranged. For this, Niels Bohr, big contribution, huge. He said that electrons, first of all, they do exist, which that's not a shock. We already knew that thanks to J.J. Thomson. Electrons exist in specific energy levels. And this is not a Niels Bohr comment, but it's going to help us make sense of this. Energy levels that we're talking about, these things are similar to orbit. Orbit. Like if we were around, the sun or something. Okay, this is the nicest model that we have right now to think about how the actual atoms look. This one that we saw a second ago with the Rutherford or Rutherfordian, you may hear me refer to it as. This is the Bohrian model instead, but they're pretty close to the same. Okay, Niels Bohr is here, and he says, all right, Rutherford, I like your idea. You're on the right track. You have a really positive ball in the center, and it's super densely packed. This is my nucleus. Okay, notice, have we said the word, let me rephrase that. Have we discussed in either Rutherford or Bohr about the specific nucleons, the things that make up a nucleus? Definitely not. Rutherford had no idea about protons and neutrons. Bohr had no idea about protons and neutrons. They just knew there was stuff in the middle. Okay, so Bohr's contribution, and this is the one that we will primarily use. He said, check it out. Some electrons hang out really close. More energetic electrons hang out a little further away. More energetic still hang out even further away. Now, these rings, these circles, these are just the orbits that we're seeing. For this particular thing, this is not going to be real, but he said, hey, we can have an electron here, and maybe there's more than one in here. We can have some electrons at second energy level, and then we can have some electrons at the third energy level. Now, this picture is not wildly different than this one, with one exception. For this picture, we can very clearly see the most energetic. How many of these are orbiting closest to the center? Okay, energy. Okay, there's only one of them. It's right here. This is the least energetic. How many are orbiting in the second level? So there's 3 of them in the mid-level. 1, 2, and 3. And I'm going to change this. We'll go out here like this. How many in the highest energy? Okay. Now, if we have higher energy still, do you think a larger level exists? Probably, right? And even more, this goes a little bit further than the chemistry that we're going to be covering. But if I said, hey, electrons have to be a certain distance from each other because negatives repel, right? The further out I go, the more energy. Do you think I have more or less electrons? Like, do you think more electrons fit in this level right here? Or will more electrons fit in this larger level? Obviously, more fit in the larger level, right? This is known as electron configuration. If you study chemistry, this is a super duper important idea. And we'll get little tiny bits of it in here, but not the whole works. Okay, this is what I will use primarily for the model of the atom. Okay, the Bohr model or the Bohrian model. Now, is he correct? He's close. He's close to our modern understanding. If we were to look at a real atom, what would we change? Like, what's wrong with this picture that's not a real atom yet? There's no neutrons, there's no protons. We only know of a nucleus, right? Something positively charged. So, modern model, and there are more people than this. Last one on our step, James Chadwick plays a huge role in this, but there are other big names that you guys have certainly either seen or will come across in your day. Maxwell is another really, really big name. Einstein, Oppenheimer, Schrodinger, all those guys are fundamental in this next part. Now, everything that we've seen so far isn't too crazy. Quantum mechanics is about to be invented or discovered, depending on your thoughts on science and math. None of the quantum world was known at this point. So here we go. Modern model. And we're looking at like 1930s is where we're at now. Okay. So a few big things. This is not all Chadwick, but he's the name that we're going to attribute to it. First off, protons and neutrons exist. Protons and neutrons exist. Okay. They both exist. They're both different from each other, but they're similar. And where do you find protons and neutrons? In the nucleus. Okay, so we have that. Okay, here's the strange idea. When we look at it, I'm going to use red for positive protons. I'm going to use green for neutral neutrons. And I'm going to use blue for electrons. Okay, it turns out that our idea of the atom isn't as nice and structured as you might want it to actually be. When I say think of a proton, anybody think of a little ball? I think of a ball when I think of a proton, but it's not quite true. When you think of an electron, do you think of a little ball? Yes. Me too. It's also not correct. There's weird stuff that happens, but we're going to go to our modern model. Check it out. This positive red thing is in the middle. And notice I'm going to try to draw it kind of to scale. What did we just draw? So it is a circle. What if it's in the center of an atom and it's red and positive? Proton. Okay, next to it, we're going to say that, hey, there's another thing right here that's green and not positive anymore. So the electron would not be touching, but I like where your head's at. What's the other one? Neutron. These are our nucleons. Okay, both of these together. This is our nucleus. And then here's where the picture gets weird. If you want to ever look at something, and this is a strange idea, if I wanted to measure how fast something was going, but I can't physically take a picture, I might be able to put something in front of it and see how much energy is transferred and then work it out from there. Like, it's a weird idea, but if all you see is a bowling ball and you know it's going to hit another bowling ball, you could probably measure the speed of the second bowling ball to try to work out a little bit of the first one, right? Here's the issue. If I wanted to measure how fast something was going and I have to do it by that collision, you could probably tell me how fast was it going. Could you tell me where it is now, though? No, because the second it hits, it's going to deflect and it's going to move, right? Or I could tell you, here's where it is, but if we don't have a way to measure how fast it's going, because anything that we do to interact with it changes how fast it's going and where it is, we can never know those two things. Do you agree with that? We can never know how fast is an electron moving. simultaneously as where is it? We can measure one of them, but not both. Okay, so here's the big weird idea. Here's our nucleus. Now, you probably don't have the ability to do this as nicely as I do, but check it out. I'm going to draw around this just a cloud. So, as we draw this cloud out, they're going to come in different shapes, and I will turn down the ink flow a little bit. Okay, for this, it's actually huge. If all I say is, hey, in that blue cloud, there's electrons, you never know exactly where they are, right? Now, for this, I'm going to try to shade that a little bit nicer, and we're not like in a quantum mechanics class. I don't think. Pretty sure we're not. Can you tell that it's darker in the... Now you definitely can. Can you tell it's darker in the middle? Yeah. And it's getting less dark as you get further away. Okay, this modern model is what we call the electron cloud model. This is our electron cloud. We can never know where exactly our electrons are. All we know is that they're somewhere in here. And there's a whole lot of crazy ideas that come out. Everywhere in this cloud, if I pick any random point, is it possible that my electron is like right here? Is that in the cloud? Okay, is it possible that it's out here? Where's it darker, in option A or option B? A. It is more likely that our electron is right there in this atom. Now, for this whole cloud region, in reality, these orbits don't truly exist. They exist everywhere all at once. It's called superposition. This is probably the appropriate time. We've kept talking about a cat that we poison, right? Maybe we poison it. We put it in a box. We put a radioactive material in there, and we're just waiting on one little beam of radiation to hit poison that kills the cat. Okay. We never know for sure until we look inside the box whether that has happened. Okay. It's a silly idea and was used to argue against it, but Schrodinger's big claim, and he was making fun of the ideas at the time, was that before we look, I can't say the cat is alive, and I can't say the cat is dead. So he concludes that, oh, right now, before we check, the cat is alive and dead. Both at the same time, which is a crazy idea. That idea of it is or it isn't or it's both is used in modern physics today all the time. Like, we use the fact that 50% chance of knowing something is one way or the other, and we just assume it's both. Now, I don't have a ton of training in this. Quantum computers, they're going to like replace supercomputers in your lifetime. It's already happening. It relies on this fact of being yes and no at the same time. Okay, in this cloud, there is a 95% chance of finding an electron. But only in the cloud. Now, notice, you say that's pretty high, but it's a weird idea. Could the electron for this atom then be out here? Outside of the cloud? What, are you sure? Because what's the chance of finding one in the cloud?
95.
So what's the chance of finding one outside of the cloud?
5.
Could it be out there?
Yeah.
It's not very likely, but it could be. It's strange. Electrons aren't real physical objects. They are waves in space, and it's real crazy. You guys should do your own digging. It gets wild. Okay, 95% chance of finding an electron. Okay, there's a lot of stuff in here. As we get through, tomorrow we are going to kick forward still a bit, but I'm going to hook you guys up. Tonight, you get homework
Oh yeah.
16.1, which you will find on page 403. Do we want a math problem? Are you sure?
We've learned math.
I'll give you the math problem out of here, or I'll give you a factoring problem.
How about only the math problem?
1 through 5.
Factoring? That's pretty.
I like factoring.
Yeah, factoring.
Cool. Get it written down. I'll post it on the thing. If you want to put anything on a note card, I would suggest name and a picture. Like, be able to identify. Like, we're not taking a quiz tomorrow or anything, but I want you don't have to remember names or years anyway, but know that Thomson is plum pudding. Know that Rutherford is dense nucleus. Know that Bohr is orbiting model. Okay, associate names with the model. We will pick up here tomorrow. We get to start talking about the actual atoms themselves rather than just what do they kind of look like.
Oh, Mr. Holler.
All right, thanks guys. Yes,
I
sir.
wasn't able to find